All right. Hello, everybody. Welcome. During the webinar, if you have any questions, please type them in the chat. There will be a few posts during the presentation or a few points rather, that we will stop during the presentation and answer questions. We'll do our best to answer them during the webinar. If we're not able to, there will be a survey at the end in which you can request we contact you to discuss further. We'll also be recording this meeting, so if you miss something or get disconnected, you can watch it later. We will send out a follow-up email with the link to the recording. So Applied Science International LLC is an international structural engineering software developer and services provider. We currently have offices in the USA, Italy, and Egypt, and our presenter today is Ayman. He's a senior engineering consultant with 17 plus years in our nonlinear structural analysis, specifically when it comes to protective design, forensic structural analysis, demolition analysis, and seismic analysis. So I'll pass it over to Ayman to take it away.
All right, thank you, Elliot. Welcome everyone to our webinar. Today we are going to speak about the anatomy of a collapse of structures due to earthquake. Um, and this will be using ELS software, which is extreme loading for structures software. Let me start by sharing the screen here. All right, so open the slideshow. Need to reverse. All right. So we always start our presentation with what we call material behavior from birth to death, or structural behavior from birth to death. Birth is when the structure is being constructed, and death when there is an extreme event that happened on the structure that leads either to a partial collapse or a total collapse of the building. Um, so the birth is when the material is in the linear stage, and the death when there is, as we said, when there is an extreme event that happen on the structure that leads to the collapse of this structure. The material goes from birth to death in many phases. First, the material is in the linear stage, then it goes to cracking, yielding, and the crushing, followed by buckling and post buckling, especially for steel members. Then it goes to the discrete phase where elements start to separate from each other, leading to debris, and these debris falls and collide with each other or collide with the ground. Finite element analysis is very good numerical method for linear elastic analysis. If you go into more details like more behavior in cracking, yielding, and crushing, and so on, you have to put some assumptions in your model because you went into the nonlinear phase of the material. For example, you have to assign the locations of the plastic hinges where are the plastic hinges are going to form. And this means that the structure is going to be nonlinear only at the location where you have specified. One other thing here is that if you go to the discrete phase where elements start to separate from each other, this cannot be done using finite element analysis or the regular finite element analysis where you are using frame element or shell element. You have to use more advanced FEM, like something like ANSYS or LS Dyna, to be able to separate the elements from each other, and then you will have debris and the collision. However, even when using FEM analysis, which is the most advanced technique, where you want to separate elements, you have to introduce what we call element erosion technique, where you remove elements from the structure to be able to reach to the level of having other elements from from the structure separate, and hence you have collapse and collision. Another numerical analysis method, which is called DEM, it's very good when it comes to element separation, debris, and collision. However, it has some problems when we are doing linear elastic analysis, or if you are trying to do something like buckling. So DM cannot be used for a steel component. That's why we came up with the applied element method. So the applied element method covers the whole history of the structure, starting from the linear phase, going all the way through the phases that we have spoken about, up to the collapse and the collision, and all of these are automated. You don't have to put some assumptions in your model, like the locations of the plastic hinges, like where we are going to remove elements. These are all done inside ELS automatically without any user intervention. It also we have also to say that in the applied element method, we don't remove elements, we remove connectivity between elements, as we are going to see later on. In this video that's in front of us, we will see the power of the applied element method. Here, we have modeled the Champlain Tower that collapsed in Miami, Florida. And this happened like 3 or 4 years ago. And in this analysis, we assumed that two columns from the bottom floor has been removed. And this leads to the progressive collapse that we see right now. The power of ELS, as we are going to see also later, that it dives into the very fine details of your analysis, like the material behavior, each reinforcement rebar inside your structure, what's happening in it, every connectivity between columns or beams or slabs, what's happening in it, every bolt or screw if you are doing steel structures, what's happening in it. And all of these are happening under the umbrella of nonlinear material models. This is the collapse of the buildings that happened in reality. We see here that the middle part collapsed, followed by the part here on the right hand side. When we also check here the debris after the collapse, so on the left hand side we see the debris of the building, and on the right hand side we see the debris coming from ELS software, and in the middle here we see a floor plan. So we see here, for example, this shear wall that was located at this part from the building. It collapsed near the part that did not collapse in the structure. This one in here. So basically, this shear wall went all the way and landed at this location in here. This is pretty close to what we see here inside the ELS software. The pancake collapse also here, we can see it. It's very clear, and it's very similar to what we see inside ELS software. So next we'll speak about what is the applied element method. So the applied element method, it is a stiffness based method similar to FEM, where we discretize each structure component into smaller elements, and then we connect those elements together with what we call material springs. These springs represents the axial deformations and the shear deformations that happens inside the material. So as I said, it is a stiffness based method, And what happened that we discretize each structure component into smaller solid elements, and then we connect those elements together with material springs, and the material springs represents the axial deformations and the shear deformations that happens inside the material. As an example, if we took here a reinforced the concrete column, so we have here two kinds of material. The first material is going to be the concrete material. Second material is going to be the reinforcement tree bars inside these elements in here. So we divide the structure, as we said, the column into smaller elements. Then let's highlight on those two elements. First, we are going to speak about the concrete material, or what we call the matrix springs. So between each two elements, at the interfaces between them, we generate what we call material springs. The material springs represents the axial deformations and the shear deformations that happened inside the material. As an example, so when we say one spring, it is actually three kinds of springs that are generated. One normal spring for the normal deformations, and two shear springs for the shear deformations, one in XZ direction and one in YZ direction. With the same exact concept, if you have reinforcement tree bars, so in the reinforcement tree bars, let's assume that we'll have reinforcement tree bars that's going to pass between those two elements in here. So in this case, probably it is a stirrup. So we replace the stirrup at its exact location inside the building, or inside the element, with again one normal spring for the normal deformations and two shear springs for the shear deformations. There are some differences between the applied element method and the finite element method. Yes, they are both stiffness based method, but there are some differences between them. In the finite element method, if you are applying a tension load on a member like this, you see that, just a second here, you see that the element deforms. However, the nodes cannot be separated from each other. In the applied element method, all the deformations are happening at the interfaces between the elements. So the element itself is rigid. So no deformations is happening inside the elements. All the deformations are happening at the interfaces between the elements where the springs are located. And the springs here represents, as we said, the material property of the element we are having in here. So, for example, if this was reinforced the concrete column and we are applying a tension load here, so we will see that these springs are going to reach to its tensile stress, and then it's going to fail. And when it fails, then we have the ability to separate the elements from each other. As for the degrees of the freedom in the applied element method, or let's first talk about the finite element method. In the finite element method, and if you are using solid elements, then you have 24 degrees of the freedom for each element, 3 degrees of the freedom at each node, and there are 8 nodes, so we have 24 degrees of the freedom. 3 for the a translation, and 3 for the rotation. In the applied element method, we have 6 degrees of the freedom, and they are in the CG of the element rather than in the node, because we don't have nodes in the applied element method. So as we said, we have in the applied element method 6 degrees of the freedom, 3 for the translation and 3 for the rotation. And this makes the applied element method solver much faster than the finite element method solver, because it has less degrees of the freedom. As for the connectivity between the elements, if you have two members that overlap in an area like this, so we have here the nodes are not aligning with each other. This is a problem inside FEM. You have to have nodal compatibility between the elements to be able to solve this. In the applied element method, this is not a problem. Any two elements overlap with each other, they are going to have springs and the connectivity in between them. And this makes the applied element method solver or the applied element method meshing much more efficient than the applied element than the finite element method. So in the finite element, if you have an area of a coarse mesh and area of a fine mesh, you have to have a transition zone in between them. In the applied element method, you don't have to have a transition zone between them. Any big element and any smaller elements in here, springs and connectivity are going to be generated automatically. And of course, the user has full control over what kind of material that is generated between two components. Let's say a masonry wall and a reinforced concrete column, so he can control what will be the interface between both members. All our material models that we use are nonlinear material models. So for example, this is a material model that we use for the concrete, and this is the material model that we use for the steel. We have also the user-defined material model where you have the ability to import any stress and strain relation in the tension and in the compression for any material, and then define what will be the failure criteria of it. Is it going to be von Mises? Is it going to be a more column, or basically when it reaches to a stress limit? So all of these are available in the user-defined material model. Finally, this is what you get if you are doing FEM, where you are trying to do collapse analysis for a, a, a structure. And this is what you get from the applied element method or from ELS software when we do a collapse analysis, where you can visually see debris and the collision between those debris. As for the software itself, we call it extreme loading for structures. So the software is divided into three modules. The first module will be the ELS modeler. The second module is going to be the applied element method solver. And the third one is going to be the ELS viewer. So the ELS modeler in here, you can model concrete columns, beams, slabs, um, masonry walls. You can model steel structures like steel columns, beams, slabs, any kind of a material, or most of the construction material exist inside ELS software. Um, then when you apply the load and when you apply the boundary condition, you send the data to the solver where we start solving the equations. And then in the viewer, you would see the results of your analysis, what's happening inside your analysis based on the applied loads and based on the geometry of your structure. So there are many applications for ELS software, starting with the anti-terrorism force protection, or what we call a blast analysis and the progressive collapse analysis. You can also do forensic engineering if you have an accident and you want to investigate the root cause of the failure of this building. You can use ELS software. Seismic analysis for new and existing buildings, wind analysis, fire analysis, can also do corrosion or the effect of a corrosion on a member or like a structure. You can do impact analysis, and finally, you can also do demolition analysis. For every numerical analysis method, there must be some verification examples. Most of the examples that I have added in here are based on like cyclic loading and really anything related to lateral loads, like a, a cyclic loading, as we said, dynamic time history analysis with acceleration records. So all the coming verification are just in the direction of earthquakes and lateral loads on the structure. We have other verification examples for like blast and progressive collapse, but currently we are going to present only this part because we are speaking about the anatomy of the collapse of the structures due to earthquakes. So the first one in here, we have shear wall under cyclic loading, and we see here the experiment. We see here the ELS model, and these are the cycles that was applied in the experiment. So we see here the analysis of ELS software. What you see in front of you here is direct output from ELS. It is not like coming from video editing tool. This is a direct output from ELS where we see here a chart between the base moment versus the drift. We see here the changes in the stiffness. We see here the failure that's happening due to the cover spalling. And when we compare the hysteresis between experiment and ELS, we found very good match between them. Next is going to be for a concentric braced frame under cyclic loading. So we see here the frame model inside ELS. We see the bracing. We see here the applied cycles. And we see here the experimental results versus ELS results. We see here that the failure happened at around 234 kips. And this is what we got in here inside ELS, that the failure was also at around 234 kips. We see here also, again, direct output from ELS. We see here the changes in the stiffness. We see here the global buckling that's happening in the bracing. We see the local buckling that's happening in the flanges and in the web of the column in here. We see here also screenshots comparing between the actual failure and the actual deformations happening in the experiment. So we see here the buckling that happened in the flanges of the column. We see here the cracking that's happened at the gusset plate here. And we see the fracture that happened at the bracing that we see here inside the ELS model. Next, we have a full-scale building for a steel structure. And in here, please note that we modeled everything according to the experiment except for the anti-collapse frame in here because we didn't have information about it. So we didn't model the anti-collapse frame in this model. We see here the analysis. We see the failures that happened at the base of the column. And we see here comparison just before the structure hit the anti-collapse frame. It's very similar to what we got. And also we see here the formations of like the bucklings that happened at the base, the bucklings that happened at the column. And this is also similar to what we got from the ELS model. We see here a comparison between the base shear versus the drift. It's very similar to what we got in here. Comparison between the deformations. We believe that this change or the difference is here is coming because we didn't model the anti-collapse frame. But in the beginning, we see very good match between them. Next is going to be a masonry wall. under cyclic loading. And this is a comparison between the experimental results and ELS results. And I think we'll stop here for the verification examples and let's move to the next set. I have one verification example that I'm going to show. And this one here is going to be about full scale building under, again, a cyclic loading. We see here the experiment, some views like an east view, a west view. We see here the actuators locations. So in this example, actually they did like two tests. One building on the left hand side, which is a the building without any retrofit, and another building on the right hand side, which has FRP wrapped around the columns at the bottom floor. So let's go ahead here and I'm going to show the analysis results. This is a comparison between the base shear versus the drift, and we see very good match between the experiment and the ELS results, not only in the terms of the drift and base shear, but also in terms of the cracking. So we see here at 0.25% drift, we see here flexural cracking at the bottom of the column, and at the top of the column in here we see here at 0.75% cracking, we begin seeing some compression failure at the columns. And also we see at 0.9% drift, also we see here cover spalling as well as reinforcement buckling. Of course, we cannot see the reinforcement buckling inside ELS because it is inside the element, but it happened. And we see here also at the failure, when the failure happened, we see compression failure that happened at the column base as well as the column top, which is equivalent to what we got from the video in here. Next is going to be, I'm going to show you here the experiment itself. It's like a video with a very long duration, but it shows the test. We see here that they are measuring the failure. This is the building that was unretrofitted, and this is the retrofitted building. Do we see the difference between them in here? Let's play this video of the ELS software also. We see here the compression failure in the column. This is the case of the retrofitting where they wrapped the columns with CFRP and we did the same thing here inside ELS, and then we see here a comparison between the ELS results and the experimental results. For ELS software, the graphical user interface is very easy, and it's something like you are modeling in a BIM tool, where you model the geometry, you model the reinforcement rebars in details. Of course, the more details you put in your model, the more accurate results you get. So inside ELS software, you can model, as we said before, RC columns, circular RC columns, beams, pre-stressed beams, masonry walls with whatever staggering and whatever bond. And this is like a complete ELS model for a very large building that we have demolished using ELS software. Using also for the steel, you can model columns, you can model beams with the connections like RBS connections. You can model cold formed steel, corrugated metal decks, bolts, and screws. And this is like a model for a steel building using ELS software. Moving also, we have some templates inside that can help the user. So for example, this is a flat a slab building where you have a template that you put the spacing in each direction. You also put the style of the column, the style of the slab, and then the ELS will automatically generate the building for you. Moving also forward, in the trusses, you can model many trusses inside the ELS, including sloped trusses, vertical trusses, the towers, and so on. Hollow core planks with its pre-stressing also can be modeled. There are like templates inside. Even on the large scale of segmental bridges, we have a template for it inside, where you can model the deck with its reinforcement rebars, with its pre-stressing. Um, so it's a very helpful tool for modeling and getting more information than you get from regular FEM analysis. So now we are going to speak about this building. This building, it's a 16-story reinforced concrete building. We see here the back face of the building. We see here the elevation of the building, and we are going to apply this earthquake on it. Uh, just to give you an idea about the geometry of the building, this is the parking level, where there are a reinforced concrete walls all over the perimeter. And then we have a core at the mid of the building and a shear wall in here. Moving up to the first floor, we see that there is a change, or there is a re-entered corner in here, where we see the floor plan of the first floor. We don't see so much walls in the Y direction. Let's call this Y direction. There are only masonry walls in the X direction, and maybe one or two in here. This is also beside the core that's in here, and the shear wall in here. Moving up into the typical floors, we begin to see now more masonry walls are introduced in the model. This is basically like an apartment building, and each subdivision in here is considered like an apartment inside the building. This is the material properties. So this is the concrete material property, the steel material property, and these are the material properties that we are, or the material models that we used inside. Um, Before we move to the actual ELS model, I'm going to show you a video for how this building collapsed. So we applied the earthquake. We see here that this part went all the way back, and this part, like, there is a twist that happened in the building. Let me play it one more time. All right. So I'm going to exit the mode of the presentation now, and let's go ahead and dive into the ELS model that we have in here. This is the ELS modeler, um, and this is the ELS model for the building. We see here all the structure components are modeled. I'm just going to hide the all the floors except for the first floor in here, and I'm going to show you how did we model this building very easily. I'm going to hide, as I said, the first or all the floors except for the first floor. And the first thing that we're going to realize in here that we have the ability to import CAD files inside ELS. So we imported all the CAD files inside, and we used them as references to model or to see what are the dimensions of the columns and the beams, so that I don't have to return back to every uh, column schedule and find what is the dimensions of the columns. Of course, we have to check also for the reinforcement rebars, but the having the ability to import CAD inside ELS and use it as a reference. Let me hide every structure component in here. So this is just a CAD file that we have imported. So inside ELS, we have the ability to import a CAD file. Then we use this as a reference. Let's first have a look on the columns. So I'm going to bring a 3D view now. And let's, for example, have a look at this column. So inside ELS software, we have the concept of styles. What is the style of the column? The style of the column, so as an example, this column I'm going to open its style. It has a geometry. So we see here that the width of the column is 300 millimeter and the depth of the column is 2100 millimeter. And it has reinforcement rebars. So we see here the reinforcement rebars, three rebars in direction 2, and then we have 10 rebars in direction 3, and each one of them has a specific area. So the rebars which are having the in this direction are phi 16, and in the other direction they are phi 14. Same as for the stirrups. There is the stirrups in here spaced at 200 millimeters along the entire height of the column. Do we see that how many branches in each direction we added? And this is like 8 millimeter rebar. Checking this, we see here that if we go to the column and we just hide the mesh, I'm going to change the mesh view or hide it. Let's make this as wireframe mesh. We see here the geometry as well as the reinforcement rebars. Apply this for every column and every beam you have. So let's have a look here on beams, for example. In the beams, we see also here, I'm going to show the style of the beam. How do you define it? So the beam is having a width of 300 millimeter and a depth of 600 millimeter. And as for the reinforcement, we see here that it has five number or five 12 millimeter as top and bottom, and it has two branches of stirrups spaced every 200 millimeters. If you are having this as a cat file and you don't have any columns in here, you just need to select a column and insert it inside your modeling window. Same as for beams. If we have beams and we are going to select a beam, just model the beam from the face of the column to the face of the column in here. And then you have the beam. You can just change the meshing of the beam from here. Let's assume, for example, 20 by 1 by 5. And then you have here the meshing that you have assigned. Same for the slabs. So if you go and show the slabs, we see here the slabs. The slab style is defined by bottom and top reinforcement. So as an example, oops, I did hide. Let's have another style in here. Let's have here the style properties. So the slab thickness is 140 millimeter, and we see here that the reinforcement rebars are top and bottom rebars, and each one of them is phi number 8. We can also see here walls. Either they are masonry walls or they are reinforced the concrete walls. Let's have a check here on this one. So let's go to the styles. We see here that it has two layers of reinforcement, and it is also phi 12 and phi 8 in the other direction. And walls also can be modeled from a point to another. Let's go to the next floor, and I just want you to see. So there is a difference between an RC wall and masonry wall. As an example, if we take this wall here on the bottom floor, so we see here from the properties and from the geometry, we assign the mesh generation as normal. Normal here means that it is a normal meshing without any staggering. And if we'll have a look on the wall in here, which is a masonry wall, and we go to the style properties, again open the geometry, we see here that the mesh generation is masonry. And when you choose masonry, it will ask you about the brick dimension. What is the length, the height, the width of this brick? And ELS will automatically generate the bricks as well as the mortar material in between those bricks. Now, moving forward to the loading and the boundary condition, we see here the first stage of loading. We made it under static load just to take into account the dead loads, the live loads, and so on. And then in the second stage of loading, we applied the earthquake. We see here the earthquake in X, Y, and Z direction. And when you plot data, you will be able to see the acceleration records for this earthquake. Please remember that if you have any questions, you can just type the question in the chat area, and we'll be able to answer it shortly. Um, Also, one of the loading options or one of the outputs that we always seek as structural engineers are the eigenmodes. What is the eigenmodes of this building? So we can go here in the in the pre-processing, and I asked ELS to give us eigenmodes like 12 eigenmodes at the last stage of loading for the on weight and the live loads applied on the uh, structure. Now let's move to the analysis results. I have here the ELS viewer. Um, you might ask yourself, how much time did it take to run this analysis up to the failure? So we are running here 26 seconds from this earthquake. So the analysis for this building up to this point, it took around 14 hours of analysis, and this was on a regular computer, not on a super computer. So if you have decided to run this analysis on something like LS Dyna or Abacus, uh, this probably is going to take from you 3 weeks, and it can be more, just to reach to 26 seconds of earthquake loading. Now, let's start viewing the results of ELS from the viewer itself. What is the viewer is giving us? So remember, when we see the video, we realized that the building went this way. Let's have a first look on the eigenmodes of this building. When we solved the eigenmodes, what did we discover? So I'm going to open eigenmodes. And remember that when we did the eigenmodes for this building, we removed the walls from the analysis just to make sure that the masonry walls are not affecting the modes of vibration of the building. And this is, of course, more conservative to do this. We added the masonry wall after we finished the the static loading, and this is another feature inside ELS software, that you can add structure component like staged construction uh, in whatever loading stage you have. So let's have a look here on the period, and we see here that the first mode of the building is actually a torsion mode. This is because we see here that all the rigidity of the structure is around this part of the building where the cores are. We don't have any shear walls or cores at this location from the structure. Pretty much every mode that we have seen for this building has a torsion mode in it. Let's say here mode 2. Again, it tends to bend rather than going in the x direction or in the y direction. This is the third mode. Fourth mode. Fifth mode. Perhaps we can view this in the 3D, and so on up till like 12 modes. So yeah. uh Now let's go and go to the analysis itself, and let's play the results and see what we can discover from here. I'm just going to play the results. We see here the vibrations. The first sign of failure that we see in here, we see cracking here, very big cracking that happened at the first floor and the second floor in here. So in order to investigate more what's happening, I'm going to hide the upper floors, and I'm going to leave the first and the second floor. Okay, so I see here also that I need to hide the slab. So I see failure in the slab, but the slab location here is hiding what's happening down there. So I'm going to hide the slab in the second floor. And we see here also that these walls are hiding the view. Let's hide uh, the, the walls in here. I'm just going to hide them because we need to only select the brick walls that I'm going to hide. Let's go ahead and I'm going to hide all these elements. All right. So let's also play the results again and see what we can discover. So we are trying to analyze what caused this building to fail. What is the origin of the cause of failure in this building? Showing now the meshing. And we begin to see here compression failure that's happening in between the elements of the columns in here. All right, so this is the first thing that I need to study. Why did this compression failure happen? Let's go ahead and I'm going to go back few frames to the back in here, and let's hide the slab of the first floor as well. And I'm going to plot the contours of the stresses in the z direction. I know that the compressive strength of the material was 3.2 and the tensile strength is 0.25. So I'm going to put these as my limits in the stresses. And then I'm going to click on apply. Let's play the results and try to figure out what's happening. So anything that turns into blue color, this means that it is compression failure. I can see here compression failure that happened at this shear wall in here. Let's go back a few frames and let's play it frame by frame or at every time step. Just showing it as solid instead of showing it as shrink. So we see here that the stresses are increasing at the corner, and we see here zipping of the compressive strength. So this means that it's turning from compression and to failure, and then it stops here. And now all this connectivity and all these springs in here failed in the compression. And then we see that the other columns, because this section here failed, they begin also to see increase in the compression. So let's rotate the structure, and we see here, let's make it this view like this, and I'm going to go back a few frames and let's play again. So after the compression failure happened at the back in here, we see that the stresses or other columns here are trying to carry these vertical loads. So we see here that the stresses are increasing, and again we find that this column is failing in compression, same as for this column. So this is a progressive collapse. What we are seeing in front of us right now is a progressive collapse to this part from the structure. You see here also collapse, or what we call progressive collapse. All right, I'm going to stop here again, and let's go ahead and dive more into the connectivity between the elements. So we said that compression failure happened. So why did it happen? How did it happen? I'm just going now to hide the second floor, and I'm going to check the connectivity at this column where the compression failure happened. Let's select an element from here, and I'm going to view the springs connecting this column to the column above. Let's first view the concrete material springs. So we see here the springs. Every element connected to another element on top of it has a 25 springs. Let's select one of those springs and plot a relation between the stresses and the strain of this spring. Chart. I'm going to put on the x-axis the spring strain, and on the y-axis I'm going to put the spring stress, and both of them I need to see the normal, not the shear, and I'm going to press on OK. So we see here the the curve of the material. So it reaches up to the compressive strength, and then failure happen. Let's also view another spring, which is the reinforcement rebar. What is the relation between the reinforcement rebar in in the column and the concrete material? So I'm going to show here. Let's select again this column. Let's go ahead and view the steel material. We see here the reinforcement rebars springs, and I'm going to select a spring which is reinforcement rebar. Let's plot a chart between the spring, again strain versus stress, and we find here that it reaches to the failure, or it yielded in the compression, and then it failed. We applied here a buckling model for the reinforcement rebar. When it reaches to a certain strain and stress, it fails, and it applies what we call the the fracture energy. Uh, Now I want to put these three pictures, or these three animations, beside each other. Let me put these as like this, and then I'm going to show also the column on the top floor. And let's animate the results here and see what's happening. Of course, I'm not going to begin from the beginning of the analysis, but just from maybe 9.5 seconds. This is the reinforcement rebar, and this is the the concrete spring. So we see here it's about to reach to failure. So it reaches to the failure, and it is now failing. We see here that the spring went into yield in the compression and then failed, and hence we see the compression failure happening in front of us. Let's view it again. Let's view it from here. So the spring reached to its compressive strength, and the reinforcement rebar is also trying to carry with it. We see here failure in the uh, in in the concrete material, we see that the bar is yielding in compression and then it failed, and hence we see the compression failure happening in here. And this happened along the entire, if we went back and show the stresses, this like happens, it starts from here and went all the way to the end of the building in here. View, just rotating it a little bit. We see here it went to the back of the building. So all the columns mainly are failing in compression. And when this happen, we actually, let's go to a side view. We'll begin to see here that the beams are now forming like a plastic hinge in here. And this plastic hinge, perhaps it is not shown in here in a good way. We see here, let's try to hide the contours. We see here that the plastic hinge is happening at the column connection with the beam, as well as at the column, uh, or at the column itself, not at the beam in here. So this means that the connection here is very rigid. Let's have a look here on what's happening else. Let's have a look here on this a connection in here. What's happening in the reinforcement rebars over there? So we see here that the column is failing at this location. Probably if we take a spring from the reinforcement rebar, we'll see that it failed in uh, the tension. Now I'm going to also dive more and let's show the core of the building. What's happening in the core of this building? Let's view all floors. And it's easier for me here to go to the input, and I'm going to show this by material instead of by type. So I'm going to hide the brick, and I'm going to hide also the slabs, the columns, as well as the girders. Let's try to understand what's happening in this core of the building. We know that the strain limit for the concrete is 0.002. So I'm going to choose here to plot strains. And this strains is going to be in the one in the compression. And let's put here the limit as 0.002, which is equivalent to the immediate a occupancy level. Let's start from the beginning. So let's try to play the results again. I will try to skip every 7 frames. Probably this is here related to the masonry wall connecting the cores together. But we begin to see here, as we see here, failure that's happening in the core very early, like at 9 seconds from the earthquake. Let's try to rotate it to the other side. until we have the failure of the core. Let's try to see also the next level, which is life safety level. Go back few frames and let's play it again. You see here cracking, cracking. Yeah, so finally, what we need to say here that ELS software is very efficient when it comes to studying the collapse of a structure. You, as an engineer, you have the ability to track every material inside your structure, every component inside your structure, whether it's columns, masonry walls, slabs, uh, whatever material that you are examining, and you have also the ability to track what's happening in the reinforcement rebars. Um, Please note also that ELS is not a design software. So if you see here, we did not design anything. We just have a design and we are evaluating this design for either an earthquake loading or progressive collapse or blast loads. So all of these are things that ELS are capable of. Um, I think we have reached to the end of the meeting. Uh, Please, if you have any questions anytime, please feel free to reach out to us. And I will, and I hope to see you next time. Thank you.
Thank you so much, Iman. And I'm dropping a link in the chat right now to a survey you can fill out to let us know how we did. Let us know now in the chat